Okay, it's so great to be here to celebrate Stefan. But like many folks have said before, this is more than a birthday party. It's like a family reunion. And I'd just like to thank all of you for being such a tremendously supportive family over all of these years. Well, maybe everybody but Martin. But actually, Martin's been super. Stefan is a rare researcher who hit a home run on his very first work. Made him celebrated around the world, and turned him into a global phenomenon. And what he is, as Dave pointed out earlier, he's just the right person to model ourselves after in this very interesting time. Mickey's talk was just very great about the enthusiasm of this move from a model-driven or Greek world, right, into a Babylonian curve-fitting world. Tremendous opportunity, but it's really important that we try to bring together these two worlds. And there's no better surfer than Stefan. And so I'm going to talk today just briefly about two directions that try to bring together the model-based theoretical understanding towards some of these data-driven methods like deep learning. So as folks have talked about yesterday, deep learning, tremendously powerful suite of techniques. We still don't understand, we don't even have a glimmer really of why these methods work. And therefore we're really proceeding according to basically alchemistic approach. And it's not even clear whether there's even really a foundational theory for deep learning, but we can try. So I'm going to talk today about what we think of as really the grand challenge of trying to understand deep learning, and that it's the fact that it's so easy to explain what goes on in a deep network locally. It's convolution, it's affine transformation, it's thresholding. These are so simple. And yet when you layer these, compose these very simple operations 5 times, 50 times, 500 times, it's just not clear at all, right, what's going on globally. So I'm going to talk just quickly about two directions to try to, instead of treating methods like black boxes, right, with millions, hundreds of millions of knobs. And of course, these black boxes, there are some who feel that they're taking us to a higher world. I would argue that we'd really like to understand what's going on inside. So two quick directions that we've been working on that I think resonate with directions that Stefan hopefully would be thinking about. The first has to do with thinking about the basic representation of data that happens in a deep network, and the fact that standard deep networks are splines, right? They're continuous piecewise affine splines. So let's just note that there are a number of people. I think Mikhail's going to talk about splines a little bit later. A number of folks in our community, in our family, are working in this direction, and I think this is a very, very productive avenue. So just really in short, if you think of a deep network, let's do something we can visualize. So imagine the input of our deep net was just a 2-dimensional vector. The output is a one-dimensional number. Then the key thing is that a deep network does two things. The first is it partitions the input space, the X space, which in this case is 2D, using hyperplanes. We'll talk a bit more about that in a second. Straight lines in this case, to create a tiling, right, of that space. And then the second thing it does is it builds a continuous piecewise affine function where it basically just puts a plane, in this case, or a hyperplane, with a slope and an intercept corresponding to each of these regions, right? And this is the output function, in this case, of our deep net. There's just a lot that can be actually said about these partitions. They're what are called power diagrams, which are a generalization of Voronoi tiling. some really interesting connections with k-means. No time to talk about that kind of thing today. And there's some interesting convex analysis. But the key thing that we have been thinking about is less about the actual function that we're fitting, but really trying to think about the computational geometry of this tiling. Okay? And the issue when you're dealing with this tiling is that you are dealing with an enormous number of tiles. So even if you just think of one layer in a network, ReLU network, where the ReLU nonlinearity thresholding has two pieces, so R equals 2, this will generate, in general, R to the K regions, where K is the number of units or neurons in your layer. That's an extraordinarily large number, right? You may have tens, hundreds of thousands of neurons in a layer. And so even just one layer, you're going to have extraordinary number of points. And therefore, there's no way we can really reason about these in the entire input space. And so one of the things that we've been doing is working on developing ways and means to actually be able to analyze and visualize what goes on in lower dimensional projections, say, of like a two-dimensional projection of the high-dimensional space. It might be the input space of a layer or the input space of an entire network. No time to talk about it today, but Spline Cam will be using this tool to visualize a lot of partitions of real deep networks. Key thing is it's a really elegant way to apply graph-based techniques to really efficiently figure out what the partition is exactly, right? So this isn't just gridding out. And therefore, it's really fast, right? Instead of hours, days to look at a partition, it's minutes. So here's an example of a Spline Cam visualization of a large, like VGGNet 16, a very large deep network that was trained to classify a number of objects, but this is the zooming in on just the area of the decision space between telling tabby cats apart from Egyptian cats. This is a deep learning talk. We have to talk about cats. And you notice a few things here qualitatively. First, a huge number of regions. Somehow much finer up at the top. They're tinier, much broader here at the bottom. And also, nearly all the regions are empty, right? The white dots are training points, okay? And these are nearly all empty, which is kind of fascinating, okay? To make things even more clear, let's talk about a particular kind of deep network that has been applied very productively over the last couple of years. This is called an implicit neural representation. Show of hands, if you have heard of these. Very interesting networks to know about. They're very low dimensional. So you have a network. The input is actually just a lattice or a pixel grid, XY points on a grid, and the output target you're trying to match is the image, say a picture, digital picture, but viewed as a landscape. So it's counterintuitive that this would be a good idea, but you can actually create very highly accurate representations of images. So again, the inputs is 2D, spatial coordinates in this case. Output is pixel intensity. You can also do this for 3D models if you're looking at shapes, right? So now the input are XYZ spatial coordinates, and the output is a binary. Are you inside or outside of the shape, right? So it's an occupancy. Voxel occupancy. Okay, so you can do, using Spline Cam, be able to understand a lot about the actual function that is being fit to represent, in this case, an object. Here are the exact boundaries of this bunny figure that's been fit by one of these INR models, visualized using Spline Cam, which in this case there's no low dimensional projection because we're just looking at the fit along the X, Y, and Z planes. And again, you can see that there are many tiles. And again, most of them are very far away from the action. Okay? So these 2 points that I've just brought up give us some hope that maybe there's a way to reason about these partitions, because again, most of the partition regions that you learn are empty. They're there because the hyperplanes were laid down in our deep network, potentially in order to classify or learn a representation to classify between two different kinds of cats. The actual regions away from our training data, away from our data manifold, might be there just as collateral damage, because hyperplanes that are intended to cross in a region of interest also might cross with other hyperplanes, right, away from the image manifold. So the emptiness of the space is very interesting. Think of sparsity, right, when you think of that. And the second is most of these tiles are very far away from the action. Okay, and the last thing I'd like to talk about with the tiling is the fact that there's a beautiful multiscale structure that can be analyzed both analytically and let's do some examples. So this is an animation showing one of these INR deep networks. And what you see is two things are happening. We're moving from layer, I'll play the animation again, we're moving from layer by layer through our network, adding more and more hyperplane cuts in our network. And we see that two things happen. First, as a new layer is introduced, we're bringing in new hyperplanes that are subdividing our tiles. They become smaller. And second, they're folded because we have to pull them back through the entire network into the input space. And let's just zoom out, and you can see, and this is a zoom in on a little piece of the representation space, but we can look at zooming out a little bit. And there's some very interesting analogs here with what goes on in multi-resolution analysis, analogous to what we might think about with wavelets. Okay? The fact that most of these regions are empty, that might appeal to you from an idea of the fact that, well, you might have a lot of wavelet coefficients required to represent an image, but most might be small or zero. There are similar analogs here as far as sparsity. In wavelets, we know we have tree structures that tell us about the correlations of large coefficients, that they tend to tumble down wavelet trees. Are there similar trees in this case? We don't know, right? The definite relationship with fractals here, fractals and multifractals, has already been exploited by Ron DeVore and others to study certain kinds of signals that are extremely efficiently representable by deep networks. And similarly, the fact that these hyperplanes can intersect very far away from the region of interest means that we should be able to capture long-range dependence. But these are all open questions. Building a theory of these multi-resolution tilings of space that is analogous to a multi-resolution in say, wavelet analysis is totally an open question. So what can we do with also with this idea of tiling? One thing we can do is we can study learning dynamics and how the partition is arranged as we do learning of a network in order to, in this case, classify. Maybe we'll just play this one again. Oops, I got to go back. We can play this one again. The dynamics of how these hyperplanes are steered as we learn using a cost function, understanding the difference between learning easy functions and difficult functions, not just in terms of training time, but really in terms of the geometry and how it's adapted. We can also think about not just thinking about knowing a deep network is doing a good job from an end-to-end perspective. That's what we do, right? We just we put in input image, say input data, we look at the outputs, and then we do some kind of training error, and if the training error is going down, we think what's going on inside must be working. Well, now we can actually understand a little bit more about what's going on inside. We can look at different metrics of this tiling. For example, the eccentricity or isotropy of our tiles. Are they becoming more long and stretched out, curvelet-like, right, along the image manifold? We can actually measure these kind of things using these techniques that we're developing so that you could make decisions. For example, a lot of graphs here, but the basic point above the top row is a smaller deep network. The second row is a larger one, and then we're comparing in the two curves just whether we use data augmentation, which is a trick for learning, or whether we don't. And we can see that the effect of data augmentation is really nullified when we go to this larger network, and that's something that you would not see from just looking at the training error, right, through the entire network as a black box. Okay, other things we can do. Eric talked yesterday about image synthesis. Well, the fact that if we have say a GAN that's based on a ReLU type GAN network, just think of a simple toy network so we can visualize two-dimensional input mapping to three-dimensional output space. The key thing is that a GAN behaves exactly like the classification networks in that you tile the input space, which in this case is the latent space, with a set of convex polytopes, and then those convex polytopes are lifted up into the high-dimensional ambient space to create a continuous piecewise affine manifold. So now if you're interested in image synthesis type ideas, it can be very interesting to know, for example, how does the volume of this purple tile here, for example, change as we go up to the manifold, because it's going to be stretched. It's that stretching as we go from in this case, the latent space to the ambient space is actually what you can attribute to a lot of deep network synthesis techniques generating biased data. Okay, but the fact now that we can actually correct for this stretching means we can actually sample in a more fair way from networks. So there's lots of applications in the synthesis. We can also use this idea, think of it like a dual of this idea, on the parameter space. If you have a continuous piecewise affine deep network, okay, that means the output is a spline. It also means that the cost function is piecewise cross entropy or piecewise squared error. Okay, so if you think of a regression network, okay, now you can actually study the loss surface because it's piecewise quadratic function. Okay, and we can actually put to rest the question of why. Everybody knows ResNets are easier to optimize than ConvNets if you're an optimization person. But it's just sort of understood from empirical standpoint. In fact, you can actually prove a theorem explaining exactly why ResNets have a smoother landscape. And it's because each of these local quadratic pieces from our piecewise quadratic cost function has a nicer Hessian matrix. You can actually prove that the singular values are better everywhere in the loss surface. Right? So this is another theoretical example. You can also explain why batch normalization, another trick, right, that's employed everywhere in deep learning. Nobody really knows what it really does. Okay, well, batch normalization is basically adjusting the tiling, right, in order to minimize the total least squares distance between the hyperplanes and the data. So it's actually crunching the hyperplanes and the tiling closer to the data manifold in order to provide better approximation. And there are a number of folks here working on scattering networks. This is something we're just jumping into now. You can actually analyze scattering networks from this approach, right? If you're using, say, wavelet transforms and absolute value nonlinearities, that's again a piecewise affine spline. And this is one example. This is a two-dimensional projection of a scattering network and a convolutional neural network. Same number of parameters in both cases. This is centered around a particular audio signal from an audio MNIST data set. And the really neat thing you see is so much more granularity, right? Fine granularity of the scattering network around our data point, which means much higher quality representation around that point, which would explain why scattering works much better in this particular case than learned convnets. Okay, just to wrap up with another direction, about 5 minutes. Okay, so another direction moving away from the tilings is to think multi-resolution analysis, but to think about how we can bring more directly ideas from harmonic analysis directly into deep networks. And let's continue with this implicit neural representation approach, where again, remember we're feeding in a pixel grid into a deep network, and the output is a that we're trying to match is an image, right? It's a picture, but it's a picture as a landscape, right? We're trying to learn that landscape. And the standard activation nonlinearities that folks have used are piecewise affine, ReLU, absolute value, bump functions, even sinusoids. But it turns out that there's when we think about this problem and the fact that we're really trying to do image representation, then it makes a lot of sense to try to think about introducing wavelets in some way. Okay, so this idea of wavelet implicit neural representations is an approach where you take this implicit neural representation deep network, but instead of using a sigmoid or a ReLU nonlinearity, you use a wavelet nonlinearity, maybe even a complex wavelet nonlinearity. So each of these sigma activation functions in, say, at this 3-layer network are a wavelet. So you basically do an affine transformation of your data, of this pixel grid, and then you apply a wavelet nonlinearity, right, independently to every output of that transformation, and then you iterate. Okay, if you do this and you take an input image that's this star type pattern, we see a very interesting pattern of the output of the first layer that might appeal to people in this audience, right? They look very sort of wiggly-like, might especially appeal to Emmanuel in a kind of a blast for the past, because these are ridgelets. Okay, and in fact, if you go back to his PhD thesis, this is actually very reminiscent of the problem that he was looking at, and so it's basically another example of this wave phenomenon. Okay, so this is an example of where you use 1D wavelets as the activation. Okay, you could also use 2D wavelets as the activation, like Gabor functions. Okay, in this case, you get curvelets as the output of this first layer, which of course not only do we know they have beautiful, powerful mathematical representation properties, but they're also very interesting analogs with sparse coding and tenuous connections with what might go on in the early like V1 layer of our brain, right? So this is really tantalizing to think of injecting harmonic analysis ideas directly into these networks. Now, this is all just talking about this first layer, but we do a multi-layer representation. So you might ask, well, what happens when we do this through two layers? I don't know, maybe Eero has some idea of what the heck is going on here. You get wacky wavelet-y patterns, or curvy patterns, okay? Totally nothing that we understand at this point. But these work extraordinarily well. Okay, so this is using this approach for CT reconstruction, and this two-dimensional wavelet approach is in the upper right, basically for just a lot of different problems in denoising, recovery, etc. These INR-based approaches using wavelets is state-of-the-art. So it's just, I think, a really exciting, because not only can we have high performance, but this is also something that we can hopefully analyze in the future and be able to really understand. Okay, so just conclude, right? There's two things hopefully you take away from this talk, maybe three things. The first is that maybe it is possible to really surf both of these waves simultaneously. I talked today about ideas related to approximation theory from this idea of the tessellation or tiling of the input space of a deep network, but there's also tremendous opportunities around the harmonic analysis side of things. So with that, I will end with my obligatory haiku. Thank you.
Yes, thank you, Rich, for a beautiful talk.
Thank you.
So that's time for a couple of questions. Lynn?
Do you think your spline can explain the hallucination of all these large language models?
Yeah, interesting. So can the spline approach explain hallucination? I think understanding hallucination requires that we understand more about just the image manifold. right? The true image manifold, and then the representation, right, or by the deep network of what it thinks the image manifold is. And so I think if there is potential, right, that if we can understand the geometry, the local geometry of what the deep network thinks the image manifold is, and that will point us towards having a glimmer towards understanding hallucination. Certainly we can say a lot of things now about, in classification problems, say about the decision boundary and about the smoothness, because we can actually extract the true decision boundary. We can talk about smoothness, we can talk about all kinds of properties about it, and so I would expect that you might be able to do the same thing in a synthetic network. Okay.
I like your observation about the resonant landscape. Can you now see ways to work backwards and make better architecture?
Yeah, very interesting. I didn't mention that. That's the ultimate goal here, right? Is a principled approach, right? Just like the first wavelets inspired us to develop new wavelets. I think, first of all, well, I'll just say two things. Yes, we're thinking about it. Yeah. And I think this is a really interesting direction because you'd like to be able to do principled design. I think, in particular, the res network tells you about maybe there are better ways to optimize, for example, that are maybe just as simple as gradient descent, or an atom-based gradient descent, but somehow are more informed about the local geometry of the loss surface. So that'd be another direction, right? A principled way to optimize.
Or better forms of geometric primitives.
Exactly, yeah. Yeah, great point.
Last question by
Yes.
Yes.
So thinking about classifiers and the knowledge that they are sensitive to adversarial attacks.
Yes.
I wonder what will be the effect of the tiling that might explain the difference between robust network and non-robust.
Yeah. So this is current something we're thinking about like right now, right? And the question being, so one direction to think about is the isotropy of the tiling around the decision boundary, right? Because that's going to, there's two things that determine how quickly you can depart, right? The function that you're fitting can depart from maybe in a non-Lipschitz way, let's say. One is the slopes of the hyperplanes that you're fitting, but the other is the tiling. Right, and so one conjecture is that in directions where there's particular adversarial non-robustness, the tiling is like malformed, right? It's yeah. So.
All right. So let's thank Rich again.
Okay. Thank you.